Now let's go ahead to learn a more generalized version of Rolle's theorem, which is called as Lagrange's mean value theorem, or LMVT in short. Now if you see, it states that if f of x is continuous in closed interval a to b and differentiable in open interval a to b, then there exists some value c in the interval a to b such that f dash of c is equal to f of b minus f of a whole upon b minus a. Now if you compare the if part of this particular theorem with the Rolle's theorem, then we see that the two conditions are exactly same, but here the third condition which was present in Rolle's theorem, that is f of a equal to f of b, is no longer required. That means here the function is not required to have the same value at the endpoints of the interval given, right? So apart from that, the other two conditions are same. Now in the then part, the LMVT says that once again there exists at least one value c in the interval a to b such that the derivative of the function, that is f dash of c, is equal to this particular expression. So now let's understand this also geometrically. What does it mean? Suppose we consider some function something like this. This is a and this is b, the endpoints. We don't necessarily restrict f of a and f of b to be the same, so therefore we keep them separate. So we have f of a and f of b. Now if you look at the right hand side expression, you will clearly come to know that it is nothing but the slope of the line joining the endpoints of the interval. So therefore it is a slope of this particular line, because the points are b comma f of b and a comma f of a. So looking at the expression, it is clear that the right hand side represents the slope of the line joining the endpoints of that interval. Now let's look at the statement once again. LMVT says that there exists a point c where the derivative at c, that means the slope of the tangent drawn at point c, equals the slope of the line joining the endpoints of the interval. So in other words, since the two slopes are same, the tangent must be parallel to the line joining the endpoints. So this particular line that we have drawn, we must have at least one tangent to the curve in the interval a to b which is parallel to this particular line. So therefore we can easily imagine that yes, there is some point somewhere in the interval a to b such that if you draw the tangent at it, it will be parallel to the line joining endpoints. So that is the geometrical interpretation of LMVT. Let's go ahead and solve one example based on this. Verify LMVT for the function f of x given by sin x, where x belongs to interval 0 to 3 pi by 4. Now first of all, let us quickly draw the graph of the sine function. The peak is at pi by 2, becomes 0 at pi. Initially it's 0. Right. Now we have to consider the interval from 0 to 3 pi by 4 only. So that is midway between pi by 2 and pi. So that is where we have 3 pi by 4. So let us skip the remaining part. I may show it by dotted lines, but it's not required. Now within this, let us mark off the two endpoints. So 0 is 1 and the other point is at 3 pi by 4. Okay? So we draw the line joining the two endpoints. Okay? Now as per the LMVT, we have to find out one point within the interval 0 to 3 pi by 4 where the tangent drawn is parallel to the line joining these endpoints. Okay, so from the graph we can clearly see that yes, there has to be one point somewhere between 0 to 3 pi by 4. Alright. Now first of all, how do we prove that logically and find out? Look at the function that is sin x. We know that it is a continuous function as well as it is differentiable over entire the domain. Okay, so the two conditions for LMVT are satisfied. Let's call the function as f of x. So clearly its derivative, that is f dash of x, will be equal to cos x. Right. Now if you see, as we draw the tangents from 0 to pi by 2, okay, so the first tangent will be something like this, and at 0 the slope will be equal to 1, so that will be making an angle of 45 degrees. And as we move on drawing tangents at the top, that is when we reach pi by 2, the tangent would be horizontal, because we know that the slope of the horizontal line is 0, and which matches with cos of pi by 2. Alright, now let us consider some arbitrary value c between 0 to 3 pi by 4. So therefore f dash of c will be of course equal to cos of c. Now as per the LMVT, it guarantees that f dash of c will be equal to f of b minus f of a upon b minus a. So therefore substituting, we get cos c is equal to f of b stands for the value of the function at 3 pi by 4, which is our b. The original function is sin x, right? So therefore sin of 3 pi by 4, we know that it is 1 upon root 2, that is same as sin of pi by 4, minus f of a. Now a is nothing but 0 in this given case, so therefore since sin of 0 is 0, we substitute that. Then divided by b is once again 3 pi by 4 minus 0. So clearly that becomes, we take 4 on top, so we have 4 upon 2, root 2 into 3 pi. So therefore we can cancel out a factor of root 2 and write it as 2 root 2 upon 3 pi. Now this particular number, it's a positive number, and the numerator is clearly less than the denominator, so therefore this particular number definitely lies between the interval 0 to 1, and this cos c represents the slope of the tangent. Now we have seen on one extremity, that is 0, the slope of the tangent is 1, and as we go up drawing the tangents at 90 degrees the slope becomes 0. So therefore somewhere in between we must have the slope as 2 root 2 upon 3 pi, which is a number lying between 0 to 1. So clearly there exists some angle c whose cos will be equal to this particular number. So therefore we have proven that there exists a value c in the interval 0 to 3 pi by 4 which satisfies or verifies the LMVT for the given function.